I'm reading this book, Theory of Functions Part 2 by Konrad Knopp. And the second part treats the case of complex analysis. Okay, so section 1 here, for example, chapter 1, entire function. Chapter number 2, so I'm here on chapter number 2 myself. The case of meromorphic functions. In chapter 3, periodic functions. So basically the case of elliptic functions and abelian integrals down there. Chapter number 4, the root and logarithm. I was reading about on page number, let me check here. Okay, chapter number 2, page number 35 here. Hey, by the way, I really recommend this textbook for those people who are interested about complex analysis. So Mittag-Leffler's theorem is down here. So it tells you basically how to construct meromorphic functions when a finite or infinite sequence of points, right, the poles, is given. Okay? So let any finite or infinite set of points having no finite limit point be prescribed, and associate with each of its points a principal part, which means a rational function of a special form. So we all know what's a principal part. They all look like this, right? So certain coefficients, when z nu here, or zn, is the singularity, this is a principal part of a Laurent expansion around that singular point z nu, all right? So then there exists a meromorphic function which has poles with the prescribed principal parts at precisely those that sequence of points. And it's everywhere else regular, so analytic, okay? So that means that the only singularities of this meromorphic function is the sequence of prescribed points down there. Okay, so exercise number 1, cotangent of z and this function 2i over exponential of 2iz minus 1 are two meromorphic functions which indeed coincide in their poles and the corresponding principal parts. So we're going to prove that here, okay? So according to the Mittag-Leffler's theorem, the first function, which is the cotangent of z, differs from the second only by an additive entire function. So we need to find this function, okay? That's the goal of the problem. So we have two functions here, f of z equal to the cotangent of z, and then we have this other function g of z equal to, what was it, 2i over exponential of 2iz minus 1. Was it? Let me check it, because 2i over exponential of 2iz minus 1. So first of all, these are meromorphic functions, okay? Notice that the cotangent of z is the cosine of z over the sine of z. So every point such that the sine of z be 0 is a pole for this function. So we have an example here of a meromorphic function with an infinite sequence of poles, okay? And each pole here is a 0 of the sine function. So that means that each pole of this function is of the form n times pi. But if you plug, like if you let exponential of 2iz be equal to 1, so you want to get the zeros of the denominator down here, then you get that the exact zeros happen exactly at those points, zn equal n pi, because 2i n pi is equal to 1, and 1 minus 1, 0, okay? So actually, f and g have poles at zn equal n pi, and only at those points. let me change my pencil for a pen down there. Okay, so what we say here is that the poles of cotangent of z happen at pi, 2 pi, 3 pi, etc., etc., and negative pi, negative 2 pi, etc., etc. So all the zeros indeed of f happen at zn equal, sorry, not the zeros, the poles of f happen at zn equal n pi for n an integer number, n in z. Okay, now the same points are the poles of this function g. All right, because there at those points the denominator here becomes 0. Now we have to prove, moreover, as per the question here, we need to prove that their corresponding principal parts match as well, meaning the principal part at each of those poles, right, of the cotangent function is equal to the principal part of the Laurent expansion of this function at those points as well, for this function. Okay, so what can we do here? Actually, we can do quite a few things. By definition, a pole of f is a 0 of 1 over f with the same order. Okay, so we're gonna find indeed the zeros of 1 over f. It's much easier. Okay, hence zn equal n pi is a 0. It's a 0 of 1 over f of z. Now 1 over f of z obviously is the tangent of z, right? Because f of z is the cotangent of z. All right, so zn is a 0 of the tangent. Now that's plain, it's obvious. Question is, what's the order? What's the order of those zeros? And remember that, okay, zn is a 0 of order, say k, order k of f, or let's change here the denomination. Let's call this function m of z. Okay, so zn is a 0 of order k of m of z if m at zn is equal to m prime at zn equal to mk minus 1 derivative, k minus 1 derivatives at zn, and all of these numbers are equal to 0, but m kth derivative at zn is not equal to 0. Okay, so obviously m of zn is equal to 0, and then m prime of z is, remember, d dz is the derivative of the tangent of z. What's the derivative of the tangent? It was secant square, right? Secant square of z. So m prime at zn, actually, the secant square is 1 over the sine square, right? So 1 over the sine square of z evaluated z at n pi. And this is, what is it? No, sorry, cosine here, cosine square. The secant is 1 over cosine, sorry. So this is what, 1 over negative 1 power n, right? Because, and then power 2. So this is 1. Yeah, because we have a square down there. So negative 1 power n, but square, we get 1. So actually, the first derivative at zn is 1, not equal to 0. Hence, zn is a 0 of order 1. So this is the important thing, order 1 of m. Thus, zn is a simple, meaning order 1, it's a simple pole of 1 over m, which is f of z equal the cotangent of z. Okay, Zn is a simple pole of f of z. Thus, we know how to compute the residue. By the way, if it's a simple pole of f, then the principal part of f at the singularity Zn, the principal part of this function f at the singularity Zn is equal to a certain coefficient here, which we call a minus 1n over z minus Zn, which is n pi power 1. And there's nothing else. Remember that the constant term doesn't belong to a principal part. It belongs to the Taylor part in the Laurent expansion, okay? So the principal part at that point, Zn, looks like this. The question is, what's the value of this constant? A minus 1 of Zn. We can write even here Zn, because this coefficient is associated with this singularity, this pole. All right? Question is, what is the value of this constant up here? Well, remember that this, for those who studied and who have taken, complex analysis, this is called the residue of f at the point n pi. So all we have to do here is to compute the residue of the function f at Zn. But there's a formula. This is the limit when z tends to Zn, n pi, z minus Zn times f, which is the cotangent, meaning cosine of z over the sine of z. How do we evaluate this limit? Well, this is the limit when z tends to n pi. So here we can perform a little trick here. Cosine of z over the sine of z minus the sine of n pi, the sine of Zn, okay? Divided by z minus n pi. Okay, because the sine of n pi is 0, so this term right here is 0. Okay, so at the limit, when you take the limit here, you get the cosine evaluated at n pi, which is plus or minus 1, and then the limit of the denominator is sine prime, is the derivative of the sine at n pi, by definition, because this is function at z minus the function at Zn divided by z minus Zn. At the limit, this is f prime, okay, the derivative of sine. So you get here, actually you get cosine at Zn divided by the derivative of the sine, which is cosine at Zn. So this is 1. Hence, the principal part at Zn of f, so the principal part at Zn of the function f is nothing else but 1, because this coefficient was computed down there, the residue, divided by z minus Zn. This is the principal part of your function, the principal part of f, the cotangent of z. All right. Now, likewise, we can prove, we can prove by the same method, right, that, excuse me, that the principal part, it's getting cold here up in Canada, the principal part now of g, remember g is the other function, g is 2i over exponential of 2iz minus 1. So we can prove that the principal part of g at Zn is likewise 1 over z minus Zn. Okay, so they have the same principal parts for any singular point Zn. So now what we have here is that the difference of f minus g is an entire function. All right, because that's the decomposition and in the theorem, right, given or provided by Mittag-Leffler's theorem here. Okay, so if m0 is one such function, meaning one meromorphic function having poles at exactly that sequence, right, then any other function meromorphic having the same poles has this form. All right, the difference between these two is just an entire function. G here is an arbitrary entire function. So the goal is to find G. In the theorem, Mittag-Leffler's theorem, this is called G entire, okay? So let's find the function. F of z was the cotangent of z, G of z, 2I over the exponential of 2iz minus 1. 2I, so G of z equal 2I over exponential of 2iz minus 1. And let's multiply the stuff by exponential of negative iz. And then what we get actually here, because we don't do nothing, this is multiplication by 1, you get 2I exponential of negative iz divided by exponential of 2iz, exponential of negative az, you get exponential of iz minus exponential of negative iz. And this is 2I exponential of negative iz over, what we get here, is, what do you call this? Because exponential of iz is cosine of z plus I sine of z, and then exponential of negative iz is the cosine of z minus I sine of z. So negative cos plus cos, you cancel these two out, and then you get 2I sine of z, all right? There, and so now you cancel the 2I, and then you get the G actually is equal to exponential of negative iz, which is cosine of z minus I sine of z over the sine of z. So you get, finally, you get here cosine over sine, you get the cotangent of z minus I times sine over sine 1. So this is f of z minus I. All right, thus f of z minus g of z is I. This is an entire function for sure. Analytic everywhere. Okay. So that's the solution to this problem out here. Now you can take it out and find plenty of interesting problems down there. The second problem you solve pretty much the same way. Try to do the same stuff, right? So determine an entire function g such that this function minus that one down there be equal to g, capital G of z entire, okay? Well, thank you very much for watching, and see you in the next one. Beautiful textbook.